Also, I'm proceeding under two assumptions today. The first assumption I'm proceeding under is that you all have at least passing familiarity with Mplus. And if you don't, that's okay, because what I'm going to do is walk you through the syntax and the commands that'll let you do what I'm going to show you how to do in missing data handling, and that's the other item that I'm proceeding under, and that is, all of you know there are two ways to handle missing data that are considered acceptable: maximum likelihood estimation and multiple imputation. And I'm going to show you a little bit of both. Specifically, what Dr. Tolan and I talked about, I'm going to give you guys 4 models. So let me back up a second. When Dr. Tolan and I talked about this, and we talked about the models that he wanted me to present, the first thought that popped into my mind, like Dr. Tolan mentioned, is that I see a lot of data from a lot of different doctors, postdocs, and so on at the medical center. So what I wanted to do is grab example data sets that I've found most challenging in my work, not only with respect to the analysis questions that are raised, but also the missing data issues that came up. So I want to pass along what I learned in dealing with these issues to you. So what we're going to do, typically the progression in structural equation modeling is path analysis, CFA, SEM, right? Usually, sort of, kind of. Well, I'm going to turn that around just a little bit. I'm going to start with a CFA model, and what we're going to see is that the sample size is very small. This is data I got from a sickle cell researcher there at the hospital with missing data. So we're going to look at a categorical confirmatory factor analysis with a covariate, otherwise known as a mimic model. The second analysis that I've gotten questions on already, moderated mediation. And I'm going to talk a little bit about the so-called MacArthur method, but what we're going to see is that with example number 2, there are 2 implicit research questions. Do you have significant mediation? And if so, is it moderated by a z or a 4th variable under investigation? And as scary as that sounds, I'm going to introduce you to some plot techniques in Mplus that makes it really easy to answer both of those questions if you know what you're looking for. The third example is a full structural equation model with a so-called latent variable interaction term. What I like about this model is that it's a full structural equation model, and we can talk through the specifics of that. But what Mplus allows you to do, for example, is create on the fly an interaction term from 2 latent variables. So not only can you form latent variables in your analysis model, you can say, give me an interaction between those 2 latent variables. So you can have main effect for latent variable A, for example, main effect for latent variable B, and you can create a latent variable A by B interaction all in one move. And you can handle missing data in an analysis like that, and we'll take a look and see how. The final one is apparently a model that's seen a lot in education, and there's no surprise, a multi-level analysis of covariance in a structural equation modeling format. Specifically, what we'll look at is a pre-post design at level 1, or the student level, and we're looking at pre-post change when, for example, a treatment or some kind of intervention designed to increase efficacy, let's say, in achievement, that randomization to treatment or control happened at the classroom level. So you've got a treatment variable at level 2, but you've got data at level 1. And if you have missing data, that can be a particularly nasty situation, but I'll show you how to navigate that one as well. 2 other items of interest. You might want to make a note that number 1, when I talk about multiple imputation, I'm going to show that there's 2 ways to do multiple imputation. The so-called alternative hypothesis model method and the null hypothesis model method. We'll get to that in a minute. Also, you might want to make another note that there's some bonus materials in folder 1 and folder 2 that I think are cool. And hopefully you will also, but it's just a little extra that I found in putting this talk together that I thought, wow, I'm not sure how many people know that, but that could be useful information. So as I go through this talk, I want you guys to keep two questions in mind. The first, we've already talked about what your options are for missing data handling. There's two of them, maximum likelihood estimation and multiple imputation. But that's not what I want you to keep in mind. What I want you to keep in mind is, what are your options? Can you use one or the other? When would you use one or the other? Why? And more specifically, as we'll see, are there certain commands and handy techniques in Mplus that are available if you go one way, but aren't available if you go the other way? And we'll talk about a particularly frustrating situation when you try to add additional information. But Mplus, for example, tells you, well, if you're going to do that, then bootstrapping is not allowed. I don't know how many of you have run up against that, but trust me, there's a way around it. So think about, when we go through these analysis models, maximum likelihood, multiple imputation, can I use one, can I use the other, what are the pros, what are the cons, and we'll talk a little bit about that. Also, put a big star by the second statement. What does missing at random really mean? And how can you make that more plausible in your analysis model? So just by a show of hands, and I gotta confess, I always couldn't stand when speakers did this, but I'm gonna do it anyway. By a show of hands, how many of you know what MAR is? Nice, very nice. How many of you hate raising your hands? Less than a third, all right, I'm doing well. Missing at random, which is the most counterintuitive name I've ever seen in statistics, if you want to know my opinion, because it's really not missing at random. What it really says is missing data on the analysis variables that you're interested in are somehow related either to the other variables you want to analyze or information you have in your data set, and that's going to be key. Because one of the ways we're going to talk about making missing at random more plausible is how to add extra information that everybody has in their data set in addition to the variables they really care about. You got a couple of dozen columns more, you always do, I know this. How can you make that information useful to you? And we'll talk about that as well. Also, a good stopping point, I think, would be between Model 2 and Model 3. So we're going to open it up at that point for a quick Q&A to make sure everybody is doing well. Nobody has something they're wondering about. Everybody gets their questions answered, and then we'll pick it up with Models 3 and 4 and have a Q&A after that. Good? Everybody hearing me in the back okay? Dr. Tolan says everybody come forward, but we sat in the back in the day, he and I. He knows that. You know that. Don't fool them.
Don't tell them.
Okay. So, also, hopefully in addition to the slides, you got 4 zip files that have all the information I'm going to go through for each of the 4 models. So the first one I'm going to talk about is a categorical indicator CFA with a covariate, sometimes called a mimic model. Multiple inference, multiple cause, which is just a CFA with a covariate. And we're going to talk about so-called alternative hypothesis model, multiple imputation, and the information you need is in the folder called Model 1 zip. So let's talk a little bit about that. This is an analysis model, as I mentioned, that I got from one of the PIs at the hospital who does sickle cell research. And they want to form this latent factor called disease responsibility. And what responsibility bears on is, for example, how well do you manage your diagnosis? How well do you manage your illness and your process through that? How well do you take your medication? How well do you refill your medication? How often do you see your doctor? Is it as scheduled? And so on. So we want to create this latent variable of responsibility. And some preliminary analyses showed us that out of the 21 items that we had, 4 of them were clankers. And that's my official psychometric term, clanker. Those items stunk. So we threw them out, and what we were left with were 17 items measured on a 1 to 3 scale that basically said, how responsible are you in, for example, taking your medication, refilling your medication, going to the doctor, and so on. So at the item level for these 17 items, we had roughly 10 to 20% missing data across participants. And as I mentioned earlier, another problem we had was the sample size. I had a whopping N of 50 to work with 20% missing data. Sounds like fun, does it not? So, just for clarification, the covariate, which is binary, is HBSS, and that's hemoglobin type SS, which is a particularly pernicious form of sickle cell disease, as in the symptoms are frequent, recurring, and often very painful. But I've got a star about this last bulleted statement, but because, thank goodness, this PI also gave me extra information in the data set, and a star is a big hint in this presentation, by the way. That's stuff you can use. They also gave me gender, age, and what's called pediatrics quality of life subscale score. So I've got extra information with which to work. That's going to come in very, very handy. So, after banging my head against a brick wall often, I found that one way I could handle the missing data is with what is so-called saturated model or alternative hypothesis model imputation. So what is that? What are we talking about? Well, the first point to realize is that multiple imputation is a model, just like an analysis model. So, saturated model or alternative hypothesis model imputation is a model with 0 degrees of freedom. It essentially imputes missing data based on a correlation matrix. Well, why is that important? Well, a correlation matrix on a basic level says everything's related to everything else in some form or fashion that is not 0, right? Well, that's going to be key because it specifies all possible relationships among both analysis and auxiliary variables, and I've italicized those because that's the key to missing at random. I've got missing on the analysis variables, I've got missing on those 17 responsibility items, but I've also got missing on things like pediatric quality of life and auxiliary variables, but I can add all of them to a so-called alternative hypothesis or saturated model imputation and use all that information, because remember, if we impute based on a correlation matrix, it says everything's related to everything else. Auxiliary analysis, everything. So I'm using all available information in the data set to impute missing data. So the answer to this next bulleted question, why auxiliary variables in addition to analysis variables, that's where we're going to revisit the issue of missing at random. And again, it says missing on your analysis variables are related to variables included in your analysis model. So your missing may or may not be related to other analysis variables, but if you've got extra information like gender, SES, and so on, these are variables we call the usual suspects in the medical center. Because if you have them, add them in, because these are variables known to affect things like adherence, attendance, and so on. So if you can include them in your analysis model, it's a way of adding what's so-called auxiliary correlates, which gives you extra information, but doesn't bias the results that you're interested in. And we're going to see how that works here in a second. But basically, alternative hypothesis imputation is a way of handling missing data by using all available information, not only from the analysis variables, but from any auxiliary variables that you have. So by throwing in auxiliary variables, I'm saying, basically, if missing data has anything to do with gender, age, or your quality of life, add it in, because every bit helps when it comes to missing data handling. So, those of you familiar with Mplus will recognize the script on the right. Those of you aren't, not a big deal. I can walk you through it. We're going to use all 17 of these responsibility or R items that have missing, but we're also going to use the pediatric quality of life, physical, emotional, social, and school subscales in addition to age and gender, and hemoglobin type SS is our covariate. So we're saying let's use everything here. But I've also put in this command auxiliary equals, and in this case auxiliary with no specifier just says keep this in the data set that you're going to spit out, or in this case the multiple data sets you're going to spit out. So in other words, don't lose SCD type. So here's the key right here, the data imputation command. And what I want to direct your attention to specifically is that C in parentheses. That's how you let Mplus know the scale of your variable, and in this case it's a 3-category or categorical response variable. So a C placed in parentheses after your variables or variable list in this case tells Mplus, okay, all these R's are categorical and hemoglobin type SS is categorical, or more specifically binary, but notice how Peds, QL, age, and gender don't have a C after them. Well, it's because they're continuous. In this case, I'm asking for 100 data sets. Why 100? Well, my sample size is kind of small. So I'm going to pump up the number of multiply imputed data sets. I'm going to write it out with a wildcard character that's going to replace this star with all integer values from 1 to 100. And put a star by this statement right here, analysis type equals basic. That is critically important, even though type equals basic seems kind of counterintuitive. Why would that be important? The answer is that's what enables missing data to be imputed based on all possible relationships between the R's, the Peds, QL, and the demographics. So let me say that again. By specifying type equals basic, you're specifying essentially a correlation imputation model that says give me all information not only from these variables, but from all the relationships among these variables. So means, variances, and covariances are all being used to impute missing data. So when Mplus writes it out, here are some key points for analyzing imputed data. Here's the big one. Put a star by this statement, because when you impute missing data and tell Mplus to write it out, Mplus does one thing that's kind of annoying, and that is in the imputed data files that it spits out, it will reorder your variables. So this first bulleted statement here says check the out file from the imputation at the bottom to see the list of the variables that Mplus put it, or the order that Mplus put it in all of your imputed data. I can't tell you how many times somebody who's better than average when it comes to Mplus, they want to go impute their data, they come back to me and said, wow, everything's gone haywire, what happened? Well, it's because they tried to use the same variable statement in the imputation as in the analysis, and they don't realize that in the imputation, Mplus may or may not keep the same order of variables. So check the out file for the imputation to see the order of the variables that Mplus has put your variables in. Then read them in that same way. The only other item of interest is that when Mplus imputes your data, I ask for 100 imputations, so I'm going to have mimic 1 to mimic 100, and that's in folder 1. But it's also going to spit out a file called mimic1list. And if you open up that list file, what you'll see is mimic1 through mimic100, the names of all your imputed data sets. So when I say type is imputation, Mplus is going to go get that list file and know that there's going to be multiple data sets to read in and analyze. So I've specified the variables that I want to use. I call the categorical variables categorical. Estimator, WLSMV. Why would I do that? Well, Dr. Tolan let me know that you guys know WLSMV is kind of a restricted information estimator, let's say. Well, if I've used all possible information in the imputation, I've gotten all the good I can out of the auxiliary variables, so I can use a restricted information estimator on complete data sets. Why not? And then I specify my model here. But again, Mplus is going to go get that list file, analyze all 100 data sets, and here's the other nice part. Mplus pools your results automatically. And it looks kind of like this. And this is just annotated output, but here are the factor loadings. And you can see they're all pretty good once you get rid of the clankers. And we can see that. Now, don't let this fool you, because with imputed data, normally two-tailed p-value is the last column you see. Well, they kind of threw you another curveball, because imputed data puts the rate of missing as the last column. So don't confuse this with p-value. And as we see, those with hemoglobin type SS are more responsible than those with other types of sickle cell disease, as it should be. So, again, Mplus pools imputed analysis results by default. So in other words, what it's doing is analyzing mimic 1, then 2, then 3, 99, 100. But you don't want 100 sets of results, but you don't have to tell it anything special to pool those results into one set of estimates. It does it by default. So here you go. And as I mentioned earlier, the first two files contain bonus information. There's extra material in folder 1 for scale reliability. So let's take a step back for a second. When you do a CFA model like this, in our case especially, we want to see if the 17 non-clanker items can form a decent responsibility scale in terms of construct validity, which is what CFAs do. Sort of, kind of. It's not the only piece of information you need, but it's a decent start. Well, if construct validity is the issue here with these responsibility items, then the very next question that gets begged is, well, what kind of reliability does it have? Well, what I've put in folder 1 is extra syntax in Mplus that will allow you to compute the reliability for these 17 responsibility items, even with missing. So if you guys want to go and check that out, you'll see that the reliability is actually pretty good. And the CFA stats are actually pretty good, even under WRMR.
Just to make sure, so it gives us the scale reliability based on how many data.
No, that's a good question. The material under scale reliability in folder 1 will give you scale reliability using maximum likelihood handling of missing data. But as a bonus assignment, you might want to see if you can get it using multiple imputation. You got all the stuff you need there. Go wild, have fun. But to answer your question, it uses maximum likelihood in handling missing data to get your reliability analyses, because it uses, for example, model constraint. Good so far? Okay, so that's an example of so-called alternative hypothesis multiple imputation. And again, it uses all available information and says everything's related to everything else, kind of like a correlation matrix, and uses all of that information to handle your missing data, even if it's item level and even if it's categorical. In the back.
The reliability syntax mentions some of the errors. What do you decide whether to ignore these Mplus errors or not?
Ah, good. I'm so glad you guys made it back there. I really am. And the question is, what you're going to get are warning messages from Mplus saying your model's not identified. That's true, because as you'll see in the file, you've got to estimate all possible covariances, all possible variances, plus 2 additional parameters in the model constraint command. Well, if you're estimating all possible covariances and variances there, you're at 0 degrees of freedom already, but then you throw 2 more in the model constraint, it's going to say, nah, I don't know if this model's identified. It's okay. It's okay. Because the warning messages you're going to get bear no importance on the scale reliability that you're looking for. Great question. So you will get warnings. Ignore them. You heard it here first. That tall guy from out of town said I could ignore it. That might work in a defense situation, actually. So, moving on. Second file. So remember, we're going from CFA to path analysis, so I'm switching it up just a little bit. But I want to talk a little bit about moderated mediation with the so-called MacArthur method. Now, do not go looking for MacArthur in citations for moderated mediation. In case y'all missed that early on, don't go do that. If you want citations, they're in here, but don't go looking for MacArthur. We don't know who called it MacArthur, it doesn't matter. The material that does matter is in folder 2 zip. So what we're going to look at is the so-called MacArthur method. So really, all you need to know about the MacArthur method is this. Prior to this method being introduced, the dominant paradigm for mediation testing was the old Barron and Kinney method. How many of you know that? I know, I'm asking for a show of hands again. I apologize in advance. It was the old Barron and Kinney method that said, well, a significant XY relationship had to precede me, blah, 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 all that stuff. That's completely been debunked by the simulation research of those such as David McKinnon at Arizona State. So, if Barron and Kinney doesn't work, then how should we be thinking about mediation modeling? MacArthur method provides the answer. The first thing that you'll see in the citations on the MacArthur method are some definitions. And they say Z moderates an XY relationship if the relationship is significant, conditional on certain values of Z. Makes sense? And M mediates an XY relationship if M explains how or why X might relate to Y. That also makes sense. But what they also talk about is temporal order requirements. So keep this in mind before you do your dissertation. Z is a moderator only if it precedes X. So what they're saying is collect data on your moderator first, and then if X, for example, is treatment control randomization, randomize only after you have your moderator data. And M is a mediator only if X precedes M. So if you put those two statements together, if you wanted to do a so-called moderated mediation analysis, you would first collect Z, then collect or assign X, then collect M. And that's very important, and that bears on the work, for example, of, what am I thinking about? Yes, thank you, Kramer. That bears on Kramer's work. So, they also talk about moderation requirements. What they mean by that is an M by X, but if you read on, they also talk about how a Z moderator by X independent variable is allowed, and a Z by M interaction is also allowed. But what they're basically saying in Kramer et al. Is some form of interaction must always be included in the linear model that comprises your mediation analysis. Why? Why would they take a perfectly good 3-variable mediation model that's nice and simple and mess it up? Why would they do that? Well, the example I'm going to show you of this analysis technique is from the so-called Perceived Media Influence, a PMI study from Talor et al. 2010. And we'll talk about the meanings of these variables in a moment, but I want to get at the question of why do you have to have an interaction term in a perfectly good, safe, 3-variable mediation model? Well, the answer is this, and it's right up here at the top at these E1 and E2 variables. What these E's represent are, for example, unexplained variation in import. And by unexplained, I mean not predicted by condition. And again, we'll talk about these in a second. And E2 refers to the variation in reaction not explained by import or condition. What van der Velde and Kramer et al. Talk about is that if you don't have an interaction in your mediation model, the result could be that these E's could become correlated, in fact, when a key assumption behind mediation is that they're independent. Think of it this way. Let's go back to good old-fashioned factorial ANOVA, right? Main effect of factor A, main effect of factor B, A by B interaction. Think about the mediator influence on the response variable as factor A. Think about the X influence on the response variable as factor B. And think about this as the so-called A by B interaction. So when you think about it in factor analytic terms, it kind of makes sense. If you do a factor A, factor B analysis of variance and only look at main effects when there's a kind of X-shaped interaction, you're going to get what looks like to be a very confusing story. But again, what the authors talk about is how not only will you get a confusing story sometimes, if you don't have an interaction in your mediation model, you can inadvertently correlate these errors. And what they've discovered is that the results you will get will be beyond bias. They will be straight wrong. So that's why you need to always have an interaction term in a mediation model. So, with that, let's talk about what these variables are representing. And again, it's the perceived media influence study by Tal-Or et al. 2010. The Y variable reaction is how willing consumers would be to buy a good or service based on a media story. So you see something on the news about something you can buy, how willing would you be to buy it? Marketing researchers do it all the time. Import stands for importance, and that's the mediator. How important a perceived shortage in this good or service would be in your decision as to whether or not to buy. Con is condition. So this was an experiment by which people were randomly assigned to condition 0, which was a less visible media story on this particular good or service, and 1 is for a more visible story. So think about seeing it on page 1 of the newspaper versus page 8 or 10, somewhere in the back. And PMI, the Z, the moderator, how inclined you believe others would be to buy based on that perceived media influence on the decision to buy. And the MZ is the mediator, which is importance by PMI interaction. So does media influence and perceived importance interact to manipulate decisions to buy? So those of you of the marketing bent will kind of get the gist of this one. So the syntax. Wowzer. Get to test my skills in walking people through it. So we've got our use variable statement here. Define is how you, for example, center covariates. And hopefully all of you have taken a regression class and know why it's important to center your predictor variables. It makes interpreting interactions really easy. So I'm going to center PMI and import, because that's my moderator and mediator. Those are the two pieces of my interaction term. But I'm also going to do something else. I'm also going to center age here. Because in addition to the variables in my analysis model, I've also got gender and age. So again, we call gender, age, and other demographic variables the usual suspects. At the hospital, that's just kind of our shorthand for make sure those are in there also, especially if you have missing data. So I'm going to center age because what I'm going to do is I'm going to create MZ, that interaction term, by saying MZ is PMI times import, but I'm also going to create what's called an auxiliary interaction, or AUX underscore INT, gender by age. And what that's going to address is the possibility that an age by gender interaction might address missing data as well. So here's my model. And it's your standard regression coefficient input for Mplus. But what I also added right here is information on how to add auxiliary correlates manually in Mplus. Now, those of you familiar with Mplus know you don't have to do it manually because there's there's a keyword in the variable command called auxiliary that we saw before, but if you put an M in parentheses after that auxiliary, it allows you to add additional information in the form of extra variables to handle missing data. But as we also kind of touched on earlier, and I want to touch on now, you can't use it because I'm asking for bootstrap test of mediation, or moderated mediation in this case. So if I try to use the auxiliary command we saw a couple slides back, Mplus is going to stop and say, nope, can't do it. So the reason I put this information here is that just because Mplus says you can't use the auxiliary M command doesn't mean you're sunk. What it does mean is that if you know the old Grand 2003 rules for adding auxiliary correlates manually, you can do essentially what the auxiliary command is doing by yourself. So, to add age and gender as auxiliary correlates of missing data, the three rules are: the auxiliary correlates have to be correlated with each other, correlated with all independent variables, covariates, mediators, moderators in the model, as well as correlated with all DVs or response variables. So what these commands are here is doing just that, correlating age and gender with age and gender, all of our predictors, and our response variable. So I'm adding it manually here because I want that information to help with missing data handling. But I don't want Mplus to squawk at me if I try to use auxiliary M. The other piece of information I've got commented out to death is the model indirect command. And just like it talks about, reaction is the DV, mod is the keyword that's going to give us a graph that's going to make it really easy to interpret what it is that we're going to find. Import is the mediator, PMI is the moderator. So you've got a bunch of values in PMI here in parentheses. And like it says, these values are 2 standard deviations below, 2 standard deviations above the mean. And that 0.1 is the increment by which values along the x-axis of the plot, we're going to see here in a second, we're going to increment. MZ is our interaction term, and condition is binary. Remember, that was random assignment, 0, 1. So like it says, ordinarily when the IV is continuous, the values would be 1 standard deviation or 2 standard deviations above the mean and the mean. But since condition's binary, it's 1 and 0. I want confidence intervals for my bootstrap test of mediation. But here's where we're going to go. Put a big star by this information here. Because as we mentioned earlier, and I'll backtrack and cover again, there's 2 implicit research questions here. Do we have significant mediation? That's question 1. And question 2 is, if so, is it moderated by perceived media influence? I'm going to show you how to answer both of those questions in what Mplus gives you in plot 3. So when you go to the output and go to plot 3, here's what you get. So let's walk through this and understand what it is that we're getting here. This red line is the indirect effect of reaction as predicted by condition, mediated by import, at values from -2 standard deviations to +2 standard deviations of perceived media influence. So if the red is the A by B interaction term plotted, what do you guys think the blue lines are? If you've got a plot of a point estimate here, what might these blue lines be? Confidence intervals. The blue lines are 95% confidence intervals placed around the indirect effect that's being plotted as a function of perceived media influence. So as I mentioned a second ago, we've got 2 research questions here. Do we have significant mediation? And is it moderated by perceived media influence? Let's go to the first question. Do we have significant mediation? Well, remember, mediation just dealt with reaction, importance, and condition, right? Or in other words, we're just dealing with those three variables, assuming PMI and the interaction have dropped out. Well, the only way PMI and its interaction term can drop out is if it's 0, right? So if I look right here at this thick vertical line at 0, that is the mediation model assuming PMI and by definition X by Z are both 0. So if I look just right here at the point estimate and the confidence interval for the mediated effect, what's the answer? Do I have significant mediation?
No.
No. Why? Because the confidence interval covers 0. That's this thick black horizontal line at 0. So if the confidence interval covers 0, non-significance is the answer. So that's the answer to question 1. Do we have significant mediation? No. The relationship between condition and reaction is not mediated by perceived importance. Second question, is it moderated by PMI? Do we have significant mediation at any level of PMI? No. At no point does this lower confidence band come up above 0. Well, that's kind of a bummer. We got nothing. Great, this guy was brought in from where again? So that's how you answer both research questions from one plot. And suddenly a moderated mediation question that can become kind of gnarly to interpret becomes really easy. At that point, now this is a good break because we're done with CFA with covariates and moderated mediation. Questions? Yes.
Obtaining the standard deviations for that variable. Let's say I have a latent. How do I obtain the standard deviations?
You
+2 and +2.
Okay. If you have a latent variable as part of a moderated mediation model?
Yeah. If it's a mediator, I guess. No. What was the PMI? Is that the mediator or the moderator?
PMI, perceived media influence, was the moderator.
Oh, the moderator.
Yeah, import was the mediator. Okay, so your question is, could you have a latent moderator? Yes, you can.
Right.
And if it's a latent moderator, then by definition it would be one of the exogenous variables, correct? So, what we'll see here in a minute is part of the way you can handle missing data in maximum likelihood is bringing in all available information, including so-called X-side variable information. So if I had a latent moderator as an exogenous variable, I should be able to bring that information into the model and it should give me a variance and a mean by default, in theory. I've yet to test that, but it's solid if I'm understanding how Mplus is handling exogenous versus endogenous variables.
So then just take the square root of the variance.
Take the square root of the variance. Nothing to it. More questions?
The Mplus handles the exogenous and endogenous variables differently. So how would it handle endogenous variables?
Okay, so the question is, Mplus handles so-called Y-side or response variable missing data differently than it handles X-side missing data. So, good question. Y-side missing data is handled by either maximum likelihood estimation or multiple imputation. But if you have so-called X-side or predictor variable missingness, then what Mplus and stat model support recommend you do is so-called bring that X information into the model. So if I back up for a second, let's say we had missing on perceived media influence, and that's an exogenous or X-side variable. So in addition to, if I can get here, in addition to the on statements that parameterize this moderated mediation model, if I had missing on PMI, what I would want to do is two things. I would want to state, in addition to PMI, condition and M by Z, I would just state those variables in the model command, and I might want to put all possible correlations between those variables in the model command also. So PMI with import MZ, import with MZ. So in that way I'm bringing in means and covariance information for the X-side variables into the model, and assuming missingness on those variables are handled by each other's variable, we should be able to maintain our hypothetical complete data sample size. So Y-side variables like reaction, just by virtue of being in the model statement, that missing data will be handled. But if you have so-called X-side or predictor variable information, those variables need to be so-called brought into the model, so you would need to state those variables and their variances and covariances so that that additional information can be used to handle missing data. I believe we'll see an example of that here in a couple of minutes. Very good question. In the back.
Does this lower the degrees of freedom or make it more difficult for the model to be identified as error?
Does it lower the degrees of freedom?
Yeah.
Specifically, are you referring to the addition of auxiliary correlates? That portion?
Bringing in the X side variable, missing variable.
Oh, bringing that information into the model? Yes, it would, because you're estimating more parameters at that point. But then it's a trade-off between, do you want that missing data handled, assuming you're in an analysis model that would be better handled by maximum likelihood. It's a trade-off between giving up a couple of degrees of freedom to get the missing data handled. My personal opinion on that is that it's worth it. I'll burn a couple of degrees of freedom, especially if the missing data, we had, 10 to 20% at the item level in the CFA case, especially as the missing data rate climbs higher, suddenly 2 to 3 degrees of freedom is a bargain.
What to do when you don't have those degrees of freedom to spare?
When you don't have those degrees of freedom to spare, we'll see an example of multiple imputation. Good stuff. You guys must have taken a trip to Starbucks before you got here. Yeah.
So I had a
Everybody's
couple
caffeinated and ready.
I had a couple questions about your first model.
Okay.
One is that there was a variable that you didn't include in the information for imputation.
Yes.
SCD type.
Yes.
What kind of variables would you not include?
Oh yeah. The question is, what kind of information would you not include as auxiliary correlates of missingness? So in this case, I threw in everything but the kitchen sink in the form of PEDS, QL, age, and gender. I'll answer it this way. Every little bit helps. Because one of the most common questions I get when it comes to auxiliary correlates of missing data is, well, what if my auxiliary correlates have missing also? Every little bit helps. Think of it this way. Go back to multiple regression class. R squared will increase no matter what you throw in the model, right? Keep that thought in mind, because think of that analogy when you talk about what variables to put in as auxiliary correlates of missingness. Every little bit helps. Now, in regression, why is it not a good idea to throw everything in your regression model? If everything increments R squared, why is that not a good idea? They do, but there's also a term called R squared adjusted that penalizes you for putting garbage in your model. But think of it this way. When you're handling missing data with auxiliary correlates, there is no R squared adjusted. There's no penalty factor. When in doubt, throw it in. Now, to answer your question, what kind of variables would you not throw in there? Well, obviously you're not going to throw in an identifying variable. That doesn't help at all. But what we aim for at the hospital, for example, when we talk about the usual suspects, we talk about age, gender, SES, things that would prevent people from coming to the hospital, for example, that absolutely would bear on missingness. So every little bit helps, as long as it makes logical sense. So don't throw an ID variable in there. That doesn't help
Is that
at all.
what the SCD type is? It's some kind of ID?
An SCD type is the manner by which we got our analysis restricted to hemoglobin type SS. SCD type breaks down all the types of sickle cell disease, but what we saw was that some of the N's, especially our overall N was 50, some of the N's for some of the other types, too small to be useful.
And I had another question, if it's okay.
Yeah.
In the next slide, sorry, one more. Why would it be okay to use, even with large levels of missing, would it be okay to use omega to estimate the score reliability?
Yeah, the question is, with such large levels of missing data, and especially a small sample size, could you calculate scale omega? Absolutely. And I know for a fact Dr. Tolan's got that syntax. Whether or not he's willing to share it, I don't know. But yes, you can calculate omega in the back.
I have several questions. I'll try to limit it to, let's stay with
Yeah.
the auxiliary variables.
Give me your number one with a bullet.
Okay, auxiliary variables. So, how do I select auxiliary variable? Let's say I have a data set, it has 500 variables, I use 50 of them, and I have missing on all 50. So, creating a missing term, like the dichotomous for each variable, gives me 50 terms.
Mm-hmm.
Then how do I select the auxiliary variables? Do I correlate each one of them with the rest of the data set to find?
No, you need not do that. The easy answer to your question is it depends on whether you're handling your missingness with maximum likelihood or multiple imputation. What we'll see later in Dr. Vajni's presentation, if you're handling your missing with multiple imputation, especially in SPSS, that's one of the ways I really like SPSS, you can throw all 450 in there and create all possible interactions for another 900 plus if you want to. I've tried to crash the multiple imputation algorithm, and SPSS can't do it, because that's what we statisticians call fun. I try to make programs crash. Now, if you're handling it with maximum likelihood, especially with auxiliary commands or manually adding the auxiliary correlates, that's another story, because you are limited to the number you can add. I've added, in my own experience, however this may or may not generalize, I've gotten as many as 22 auxiliary correlates in a maximum likelihood estimation, but other analyses under other circumstances I've had to go with as many as, or as few I should say, as 3. If you're adding a saturated correlates model on top of your analysis model, you can see and kind of imagine the circumstances under which maximum likelihood would kind of struggle with that. So it depends.
I was wondering about how you select.
Classic statistician answer, it depends. Done. Over.
So I was wondering how you select those auxiliary variables. If one of the conditions is that they are to be correlated with the missingness on the variable, what if they're correlated with missingness on some but not correlated with missingness on others?
Then you would go with the auxiliary correlates that are most highly correlated with the most missing data on the most analysis of variables that are of interest. Then it's a matter of pick your poison, especially if you're using maximum likelihood handling. Then you only want to include the auxiliary correlates that are most highly correlated with your missingness. So you've got a wealth of information to choose from, but I'm pretty sure you could narrow it down quickly with a correlation matrix. It'll tell you which ones are most highly related to the missingness and which ones aren't. But the upside is this: there's research out there by Enders, Matza, and Ruhlman that says you don't have to have a whole lot of auxiliary correlates in maximum likelihood. 5 to 7 will increase your statistical power dramatically. Good? SEM. Well, that was moderated mediation. So let's go to SEM, latent variable moderator. And again, we're going to use alternative hypothesis imputation, and that's in folder 3.zip. And here's what I'm talking about when I talk about a latent variable interaction. This comes from the so-called YWLP study, or Young Women's Leadership Program. It is a college/community-based mentorship program by which college graduate students mentor teenage youth in the community towards some community action or service-oriented positions, let's say. So what this particular researcher wanted to look at was they wanted to form a latent variable that quantified how active each teenage participant was in the YWLP program. So these 12 items just get at how active were you in the program? Did you attend the meetings? Did you go to the community action meetings and so on? RELMen is kind of the flip side of the mediation, or I'm sorry, the mentorship, I've still got mediation on the brain, is the flip side of the mentorship coin. So if we're looking at how active were the teenage participants, we also need to look at what was the relative quality of mentorship, which is what RELMen captures. So these are responses also given by the teenagers as to their perceptions of how well their big sister in the program mentored them through it. Change is a 15-item latent variable that just quantifies how teenage participants' attitudes, beliefs, behaviors changed as a result of being in this community mentorship program. But what this particular researcher also wanted to do is see if it was possible to test whether or not the YWLP participation and relative mentorship quality interacted to produce change. So in other words, is it just additive or is it interactive? So this big black dot in the center of this analysis diagram is the YWLP by relative mentorship interaction term. So the reason this is interesting is because we're forming latent variables from items just like we saw previously with responsibility, for example. Well, what Mplus allows you to do is not only form these latent factors, which are going to comprise main effects. So again, let's go back to factorial ANOVA. Factor A, factor B, it kind of begs the question, is there an A by B interaction? You can test that, even in a latent variable model. And in this case, you can test it even in the presence of missing data. But why would I use alternative hypothesis model imputation? Well, the answer is there's something called Graham's Golden Rule of Imputation. That comes from his 2012 book. Graham's Golden Rule says if you're going to use multiple imputation, your imputation model, and remember your multiple imputation is a model just like an analysis model, but Graham's Golden Rule says your imputation model has to be at least as complex as your analysis model. Well, there's no way to get a latent variable interaction in an imputation model prior to imputing the missing data. So if I'm going to follow Graham's Golden Rule and make my imputation model at least as complex as my analysis model, I need a saturated or alternative hypothesis imputation model. I need to use all available information at the item level to handle missing data for a latent SEM interaction model. So here's what that looks like. All of our variables are categorical. They're kind of Likert scale. How much did you participate in the program? How well did your big sister mentor you in these areas and so on? They're all on a categorical scale. But I want to draw your attention to two commands right here in analysis. You need type equals random to create a latent variable interaction, because we're taking the variance from two variables that are made and formed by the model command to create a third variable that isn't made in the model command. But random allows you to do that. I'm not going to get into numerical integration. Not going to do it. But bottom line, we need integration because we've got latent factors behind categorical indicators. So, for all of you, what integration means is get comfortable when you hit the run command. I only use 10 imputations, as y'all will see in folder 3, and I ain't going to tell you how long that took. But I did run it ahead of time, and it did converge, which was great. So we've got our latent factors here formed by the by command. By is how you parameterize a CFA, measured by these items. But here's the key command right here, int bar relmin xwidth ywlp. Well, I'm going to form a variable on the fly in the analysis model called int or interaction, and this bar is Mplus keyword notation for measured by, so I want an interaction term measured by relative mentorship interacting with YWLP participation. So then I can look at, for this change response variable, the two main effects and the A by B interaction. Good? So when you run it, again, we've got annotated results, so you'll get loadings for all of your latent factors. I just show change here, but you'll get loadings for all your latent factors. But here are the regressions that we're interested in. So again, rate of missing, don't go over here and conclude you don't have anything significant. Don't make that mistake. Two-tailed P is the next to the last column, and it looks like, in fact, change is an additive or main effect process because we have significant main effects for YWLP and relative mentorship, but it's not interactive. But the key idea behind this analysis model is we can test an interaction even between latent variables and with missing data all in one step. Good?
Got two questions for you.
Nice.
Is the xwidth
Now I've got Dr. Tolan
Subcommand.
involved. I must be doing something right.
only applicable when you're doing latent variable interaction? Or, yeah. What is that? So xwidth is only applicable with the bar with the type equals random command. Can I
Yeah.
do that with observed manifest variables?
Okay, what Dr. Tolan is asking here is that there are lots of different ways to create interaction terms. We saw in the moderated mediation model a second ago where I used the define command to both center my predictors and to form the M by Z and the age by gender interaction. Well, I used the define command because all those variables were observed. The reason you need a specialized command like xwidth is because prior to the model command forming those latent variables, YWLP and relmin, those variables don't exist. So the rule in Mplus is that if you want to create an interaction term from observed variables, you use the define command. If you want to create an interaction term from latent variables that are formed from the model command, you have to use int or the bar measured by an xwidth, but don't forget type equals random.
Say that again.
Yes. Now I've hit on something. This is great. If you want to form interaction terms in Mplus, you use the define command if at least one of the terms in your interaction is observed. So if at least one variable is an observed variable, you use define. But the reason we need xwidth in this case is because both of those latent variables are unobserved prior to the model command. So if the variables in the interaction are unobserved, you need xwidth, or interacting with type equals random. Yeah?
Just to make sure I'm getting that, so xwidth is like an operator, it's not a variable.
Yes.
Okay.
Excellent point. Xwidth is a keyword operator that works together with the bar, which is, again, measured by, and with type equals random. So those three together, type equals random, bar, and xwidth, tells Mplus, whoop, I'm not done. I got to create an interaction term based on latent variables, add it as a predictor, then get slope estimates here, which is what we're really after. But yes, xwidth is a keyword operator, not a variable. Yes?
Second question.
Second.
just as a note, the INT can be called anything, right? You can call it
Yes.
James or Mike or Bob or Bill, whatever. Now, the other question I have is that I know from many readings, sometimes people will say, I did my regression analysis and I tested my interaction, it was non-significant. In your case, the interaction is non-significant.
Yes.
Let me just drop it. What's your thought on that?
Dr. Tolan's trying to sucker me. That has to do with the issue of model trimming. And what I mean by model trimming is you've got this model that you want to test. We think we know what produces change in community teenage females. We think it's participation in YWLP and the quality of mentorship, but we also think it might interact and not only be an additive main effect, but an interactive phenomenon that produces change. That's my theoretical model, and that's important. Because research is, you go all in, to use the poker term. If that's your model, that's what you test. If you get non-significant results, you get non-significant results. Model trimming comes from the work of McCallum way back in the day that you don't even want to know about, but I'll bottom line it for you. Model trimming is this idea of, well, maybe I get a better fitting model if I just start taking all those large p-values and chucking them. Well, you can, but what McCallum found a long time ago is that it's an unreliable way to find the exact population model that's producing these relationships. Because remember, we talk about these estimates as parameter estimates. Parameters mean what's going on in the population. What does the population say about these relationships? McCallum showed that if you start taking non-significant slopes like this one and chucking them, you're no better off in finding the population model that produced this sample data. But really, when you think about it, it's intuitive. We propose a model and test it to try to find out what's going on in the population. Sometimes you get non-significant results. But assuming a simple random sample acquired adequately from the population of interest and so on, that should tell you you need not look for an interactive effect anymore if you want to produce change in community females. So, no, don't do it. Bad, Michael, bad. Need like an 8-foot ruler. Yes.
Back to this interaction, you said if
Yeah.
you're involved with at least one observed variable had to be done and defined,
Yes.
but latent variables don't exist by then. So what if you wanted observed by latent interaction?
If you want it observed by latent interaction, I believe it is still the define command as of version 7.
So I could put my latent variable inside the define command.
You can, but it would have to be then, I would have to take INT and put it right there. It would have to be the last variable in the variable list, because I don't know if you guys noticed earlier, but these auxiliary correlate variables that I created are the last ones in the list. So if you create variables by the define command, they have to be the last ones in the use variables list.
So if I understand what you're saying correctly, if
Yes.
there's any partiality of the interaction being created from a manifestation with even a latent variable, right?
Yes.
I have to add that into the end of my use variable command,
Yes.
and also then I can use define.
Yes.
Set it up.
Yes. But if both variables are latent, you don't need any variable statements. You need model keywords like X with.
Let's go with one more question before the last example.
I
Yeah.
just wanted to know the way I run it. Observed and latent, I always run it with X with.
Okay.
So I'm not sure if the define will work.
What version are you running it with?
7.4.
7.4? Okay. Let me check on that. I'll get back with you on it.
It runs with X with. I don't know if it has two alternatives.
Do you put the observed variable in the define command to center it prior to running it that way?
No. I thought the X with does that.
Let me check on that. Let me check on that one. We may need clarification on it. Let me check on that and get back with you guys. That's a good question. Yes.
So in this lecture, you use the example of categorical variables that have missing data. So
Yes.
can you use the same method to deal with the missing data for continuous variables?
Absolutely. Yeah, the question is, the examples are looking at items measured on a categorical scale with missing data? Absolutely you can. I chose categorical variables because this is psychometrics. You guys are psychometrically inclined, I'm guessing, so you deal with item responses that are most likely on a categorical scale. But yeah, that's a great point. Any of the methods that I show you here can most certainly be used with continuous data. And the last one, a multi-level ANOVA. And again, this bears on the situation where, for example, you're trying to increase academic achievement. You give a pre-test to students, you administer a treatment, and then you give a post-test. So I call it ANOVA because one way to analyze that is to look at differences in post-test scores as a function of treatment versus control after controlling for pre-test. But the only wrinkle that we've thrown into this example is that students from which we get pre and post-test scores are nested within classrooms. Why would that be a problem? What's the big deal? Why not just run your ANOVA, throw treatment in there, and see what you get? Why is the idea of students within classrooms a problem? Yes, those observations are not independent. One of the key assumptions behind traditional analyses like analysis of variance and analysis of covariate offshoots, multiple regression, and so on, is that all the responses are independent. But if you're looking at student achievement from students nested within classrooms, each student in the same classroom is going to have a score that's somewhat correlated with the achievement score of everyone else in the same classroom. Why? Same teacher, shared experience. So the key idea here is that the responses pre and post are non-independent because of a shared experience in the classroom. So what do you do then? Well, now we're going to talk about null model imputation. So we talked about alternative hypothesis model imputation is everything's related to everything else. All the analysis variables, auxiliaries, all information on the table ready for imputation. I'm going to show you in a second why we need null model or analysis model imputation. So let's get a better idea of what we're dealing with here. As I mentioned, we've got pre-test and post-test scores at the student level. Now, don't let this terminology throw you. SEM adherence, we'll call that the within level. So if you go looking at the Mplus user's guide, it'll call that within. Okay. If you go to HLM, hierarchical linear modeling adherence, they call that level 1. Okay. Same thing. So at the student level, we've collected pre and post-test data, and we're calling this a multi-level ANOVA because we're going to look at post-test differences after controlling for pre-test as our covariate. So this big black dot right here says that because students from the same classroom are going to have correlated scores, there's going to be variation in the average post-test score across all classrooms. That's where we get level 2 or between or classroom level variation. So we're going to bring that down here and call it a latent variable. And it's latent because we don't know how much variation in average post-test scores occurs across classrooms, but we're going to get Mplus to estimate it. But we need to bring it down to the classroom level because treatment versus control random assignment occurred at the classroom level, not the student level. So the level you randomize is the level you analyze. Old intent to treat saying, but is very applicable here. If you randomize at the classroom level, you have to look for an effective treatment at the classroom level. So in this case, we're looking at the extent to which treatment explains variation in average classroom post-test scores. And these E's, again, are unexplained variance. So this is the variance in post-test at the student level not explained by pre-test And this EB, or error between, is residual variance in post-test not explained by treatment assignment. So far, so good. Basic HLM. If you have seen it, good. If not, no big deal. That's the basics of HLM. But the key question is this: why do we need null model imputation? Why can't we just say everything's related to everything else? Treatment, pre-test, post-test? Why not? Well, again, it's because these responses are nested within each classroom. So within each classroom, the responses are non-independent. So before we run our analysis, we need a way to handle missing data that basically says we don't have a simple random sample, we've got a cluster sample. Or in other words, we've got students sampled from within clusters or classrooms. Another way of saying it is this: a simple random sample assumes independent responses or an intra-class correlation of 0. Well, with nested responses, we're going to have some post-test variance occurring both at level 1 and level 2. So that's a non-zero ICC. So the key idea behind null model imputation is there needs to be a way to say we don't have a simple random sample or an ICC of 0. We've got a non-zero ICC, or that some of this variation in post-test scores occurs across classrooms, not just across students. So we need model-based multiple imputation. What that means is it's not going to impute saying pre-test, post-test treatment, correlation matrix, everything related to everything else, go. No. It's going to say that these post-test scores show variation across students and it shows variation across classrooms, and we need to preserve that before we handle missing data. Good? So for those of you attending Dr. Vajni's talk later on today, I'm going to show that this situation is a perfect example why SPSS imputation is bad. But that comes later today. So, here's how you do null model imputation. The setup is the same way. We're still going to list our variables, say which ones we want to use, but we've got to specify which variables only occur at the student level or within, which is pre-test. And we have to specify which variables only occur at the classroom level. Well, that's group or treatment group is how I've called it, because that's where random assignment occurred. And the cluster is class or classroom. So far, so good? Here are the key statements. Type is 2-level. Well, it is. We got student and classroom. But here's the really important statement. Estimator is Bayes. Now, I'm not going to give you the 5 minutes on Bayesian estimation because you need a whole lot more than 5 minutes. For our purposes here, this is how you initialize null model or model-based imputation. Estimator Bayes. Because then what happens is Mplus is going to look at your model statement and say, okay, we're regressing post on pre, and we're regressing post-test variance at the classroom level on group. Okay, we've got a non-zero ICC, we've got variation at both levels. Then I'm going to come back with data imputation. So with estimator Bayes, type is 2-level, and data imputation after the model command, that tells Mplus, use this model and the relationships among the variables implied within it, then impute my missing data. So it's not going to use all possible relationships between pre, post, and treatment like we've seen previously. It's going to use the model specified relationships between these variables at the student and at the classroom level. Then it's going to impute missing data. And when you come back with an analysis command that just reads the imputed data back in that we've already seen, we can see that group does improve achievement after controlling for pretest differences. But again, the key idea behind this example is that we have to switch to null model imputation. There has to be a way to tell the program we've got students nested within schools, and we're testing a specific model at both the student level. We want post-test scores controlling for pre-test differences, but we also want that variation across classroom to be predicted by treatment group, because treatment occurred at the classroom level, not at the student level. So by those commands we saw previously, Mplus is going to say, okay, here are the relationships among your variables that I'm going to use when I handle your missingness.
So the missing data is both the pre-test and the post-test?
Yes, good question. The question was, is the missingness on the X side and the Y side? In this case, Y side would be post-test missing. Yes, there are. X side would be pre-test missing. Yes, there is. So there's missing on both X and Y side, which means there's missing not only at the within or level 1, but there's also going to be, by extension, missing to an extent in level 2. Yeah.
How complicated does this get if you want to add auxiliary variables?
How complicated does this get if you want to add auxiliary variables? Great question. Very. Isn't that great? We got 2 answers for everything, right? It depends and very. That's it. That's all we need. To answer your question, if you have auxiliary correlate information at the student level, you can add that here using the 3 rules we saw earlier. But if you also have classroom level auxiliary correlate information like some indicator of procedure, teacher efficacy, teacher experience, list goes on, you can add that here manually like we also saw. But it can get really complicated really fast. And as I mentioned earlier, even under simple random sample situations, you can't go crazy with your auxiliary correlates, especially in maximum likelihood. But you can see how that would very much be the case when now you're splitting a covariance matrix, essentially, which is what's going on here at 2 levels, and then throwing auxiliary correlate information in there. In theory, you can. Have I personally tried it? No. But give it a shot. That's the other answer I would have. The worst thing Mplus can do is croak. And it's going to do that anyway.
What if the classes are in different school, so it's a 3 level?
Ah, great question. What if the classes are then nested within schools? So you have a random sample of schools. Within those schools, you randomly sample the classrooms. And within each classroom, you have X number of students. That's a 3-level model. So in Mplus, there's a command called type equals 3-level, which can handle it that way.
Is the cluster then school? Cluster is school?
Well, you have 2 cluster variables at that point,
Okay.
because you're going to see between 1 and between 2.
Okay.
So between 1 would be classroom, between 2 would be school.
Okay.
And I just happened to publish a paper on that recently in Dr. Vajni's Journal of Early Adolescence on 3-level modeling.
Okay.
So it can be done, and I show how to use, and I show how to do it in Mplus.
Oh, great.
Can be done. You can do it that way, or let's make this a little harder. What if you've only got 2 or 3 schools and schools not of interest? You don't have any. I guess I'm done with the pointer. And class dismissed. Thank you. What if you've only got 3 schools and schools not of interest? You don't want it.
Just teachers, yeah. Okay.
Yeah, that happens a lot. School is a nuisance.
Okay.
You want teacher information, you want student information. There's a command called type equals complex 2-level, where you declare school as a complex variable, and complex means I want to ignore it, but I don't want to bias my parameter estimates because I'm only interested in teacher or student. you can use type equals complex 2 level. And in that case, level 2 is classroom, level 1 is student, and school can be ignored, but you don't have to worry about getting biased parameter estimates in the output.
That you pay for?
No, no, but it's in the Mplus user's guide. Type equals complex is the command, and it shows how you can do that even for a 3-level model. Meanwhile, I'm gonna see if, while I take more questions, I'm gonna reassemble the pointer. So, more questions.
Let's do 2 more questions and we'll close out.
I'm assuming we have. Yes, in the back.
Can we apply that to the couple data?
I'm gonna do this while repairing. Couple data.
Couple data?
Dyadic data?
Yeah, data.
Dyadic data. Yes. Another excellent question. Dyadic data is a special form of 2-level data, whereas relationship partners are nested within the relationship, right? So the relationship comprising the 2 partners is the between level, and the 2 partners are, and the differences, let's say, in their, or the possible differences in their response variable score occurs at the within level. Yes. Yes, you can. Dyadic data is just a very special form of nested data where the level 1 sample size, or the within sample size by definition, is restricted to 2. Now, be careful when you analyze dyadic data, because with 2 as a sample size at the within level, how many degrees of freedom do you have? 1. So be very careful how you analyze dyadic data. But the good news is the Mplus manual has, for example, analytics on twin studies, genetic twin studies. But there are other examples out there. It depends on whether your dyads are so-called distinguishable or indistinguishable and so on. There are papers out there that address that. I got one out there on that issue also, actually, that shows how to handle dyadic data. But yeah, dyadic data is just a special case where the n at the within level is 2, and only 2. Good stuff. Do we have another? I didn't notice. Do we have another one?
Well, then, hey, Jansen, with this, thank you so
And
much.
the printer and the pointer works. Yeah. Thank you.